Welcome back. You know what we do here? We find interesting, sometimes dense machine learning research, and we break it down for you.
That's the plan.
So today, we're diving into a really fascinating paper that tackles a pretty persistent headache with these big vision language models, the LVLMs.
Yes, the ones that can look at a picture and tell you what's in it. Usually.
Usually is the key word. We're talking about when they confidently describe things in an image that just aren't there. Object hallucination.
Right, and it sounds maybe a bit funny, but it's actually a serious hurdle. If we want these models to be reliable, for actual applications.
Like really rely on them.
Exactly. Then having them just invent objects is a major blocker for trust. Imagine using one for, say, accessibility, and it describes a hazard that doesn't exist or misses one that does because it was busy hallucinating something else.
That's a really good point. So this paper offers a pretty clever way into this problem, doesn't it?
It does. The title is TruthPrint, Mitigating LVLM Object Hallucination via Latent Truthful Guided Pre-Intervention. Quite a mouthful.
Yes. Academic titles for you.
Mm-hmm.
But the core idea is really neat. They're essentially trying to peek inside the LVLM's brain while it's generating the description.
Looking at the internal states, the hidden layers.
Yeah, to see if they can spot like an early warning signal, a sign that the model is about to make something up and then step in.
And what's exciting, I think, is especially if you've been following work on large language models, the text-only ones, is that this builds on similar ideas there. Researchers have been probing LLM internal states to see if they reflect, truthfulness or knowledge.
So this is extending that to the visual side, the vision-language connection.
Precisely. It's trying to understand that much more complex interplay. It feels like a very natural and important next step in trying to get a handle on these incredibly complex systems.
Okay, so let's break down what the paper actually does. They start naturally by framing the problem. Object hallucination is a big deal. It makes LVLMs less trustworthy.
Standard setup. But then they highlight this gap. People have looked at LLM internal states for truthfulness, but it wasn't clear if LVLM states could give you that fine-grained, like per token signal for hallucination.
Oh, okay. So not just this whole description might be dodgy, but this specific word is likely made up.
Exactly. And that's way more useful, right? If you can catch the error right as it's forming, you have a much better shot at actually fixing it, or at least flagging it precisely.
It's like knowing which ingredient made the soup taste weird, not just that the soup is off.
Good analogy. So to test this, they set up some experiments. They took a few well-known LVLMs, Mini-GKC4, Lava 1.5, MPLELL2.
The usual suspects.
Right. And they fed them a bunch of images, asked them to generate descriptions. Standard stuff so far.
But here's the clever bit, the labeling.
Yeah, this is key. For every object the model mentioned in its description, they looked at the model's internal state, the hidden state vector, for the token that came just before the object word was generated.
Okay, the preceding token state. Why that one?
The intuition is that the model's state, just before it outputs a word, should contain information about what it's about to say, including potentially whether that thing is grounded in the image or not.
I see. So they grabbed that state and then they labeled it how?
Simple labels. Truthful, if the object mentioned was actually in a reliable ground truth description of the image, and hallucinated if it wasn't.
So they built this data set of internal states, each tagged as either leading to a true statement or a hallucination, like trying to catch the model red-handed internally.
Sort of, yeah. And what they found was, pretty interesting. They trained a simple detector on these internal states. Now, it wasn't perfect. It couldn't catch every single hallucination.
Okay, so limited accuracy overall.
Limited recall, perhaps. But the specificity was extremely high.
Specificity, meaning few false positives.
Exactly. When the detector did raise a flag based on the internal state, it was very, very likely that the model was indeed about to hallucinate. Low false alarm rate.
That's crucial because you don't want a system that's constantly crying wolf and stopping the model from saying perfectly correct things.
Right. They measured this using something called the likelihood ratio for positive results, LR plus 2. And they got values close to 20, which statistically speaking is a strong signal.
Okay, so maybe like a smoke detector that's incredibly reliable when it goes off, even if it sometimes misses a tiny bit of smoke.
That's a decent analogy, yeah. High reliability when positive, even if not perfectly comprehensive. That high specificity is really the first P finding.
Got it. What was the second main discovery?
This one's maybe even more profound. They noticed that these patterns associated with hallucination, the way internal states looked when leading to a false object seem to be similar across the different LVLMs they studied.
Wait, really? Even though they have different architectures, trained differently?
Yeah. It suggests that these models might be encoding hallucination-related information in sort of common ways within specific shared mathematical spaces. They call them latent subspaces. They even talk about identifying generic truthful directions that seem to be shared across models.
Wow. That hints at something more fundamental, doesn't it? Like maybe there's a basic way these combined vision language systems represent real versus made up.
It could be.
Yeah.
It suggests that the phenomenon isn't just some random quirk of one particular model, but might relate to how they handle the grounding of language in visual input more generally. A very intriguing finding.
Okay, so based on these two big findings, high specificity internal signals and shared hallucination patterns, they built their solution, TruthPrint.
Right. Truthful guided pre-intervention. It's a two-stage approach.
Stage 1.
Stage 1 is learning. Using that labeled data set of internal states, they essentially map out that truthful direction in the model's latent space. They learn to distinguish the truthful state patterns from the hallucinated state patterns.
Okay, so building the detector, basically. Learning what truth looks like internally.
Exactly. Then stage 2 is the intervention, which happens during inference time, when the model is actually generating a description for a new image.
This is where it gets active.
Yes. As the model generates token by token, TruthPrint monitors the internal state before each potential object word. If the state drifts too far away from that learned truthful direction, if it looks like it's heading into hallucination territory,
It steps in. What does it do? Just block the word.
it's a bit more sophisticated than just blocking. It can reject the likely hallucinated token, but it also does this clever trace back.
Trace back.
Yeah, it looks back at earlier tokens generated in the sentence, particularly ones where the model might have been less confident. The idea is that maybe an earlier, uncertain choice set the model down the path towards hallucination.
Ah, like the hallucination didn't come out of nowhere, but was triggered by a previous wobble.
Potentially, yes. So it identifies those earlier lower confidence points and essentially forces the model to reconsider. It selects the next most likely token at that earlier point, trying to steer the generation back onto a more truthful track.
So it's not just stopping the bad word, it's potentially correcting the sentence's trajectory earlier on. That sounds quite smart.
It's a neat mechanism. It tries to fix the root cause, not just the symptom.
Okay, that's TruthPrint. But they also introduced something called Calm Hallu. What's that about?
Right. Calm Hallu tackles transferability. You've got TruthPrint working for, say, level 1.5. But what if you want to apply a similar idea to a brand new model, or even just a different version? Do you have to retrain everything from scratch?
Yeah, that would be a pain. And expensive, data-wise.
Exactly. So Calm Hallu, which stands for Common Hallucination Subspace Alignment, tries to bridge that gap. It leverages that finding about shared hallucination patterns.
Ah, the second discovery.
Yes. The goal is to align the latent subspaces related to a hallucination between different models or different data sets.
How does it do that, in simple terms?
Basically, it identified some key directions or base vectors that define this hallucination subspace in both the source model, where you trained your detector, and the target model, where you want to apply it. Then it learns a mathematical transformation, usually a simple linear one, to map the target model's internal states into the source model space, or vice versa.
Okay, so it's like learning a translation dictionary between the internal hallucination languages of the two models.
That's a really good way to put it. It allows a detector trained on one model to be more effectively applied to another, even if their internal workings are somewhat different. Makes the whole approach much more practical and scalable.
That definitely sounds useful. So did it all work? What were the experimental results like?
They seem pretty strong, actually. They ran extensive tests using several popular LVLMs, including newer ones like Win2VL and InternVL 2.5, which have different architectures, and evaluated them on standard hallucination benchmarks like Chair, Popey, and Alava Bench. And TruthPrint significantly outperformed the existing state-of-the-art methods for reducing object hallucinations across the board. That's the main takeaway.
Better hallucination reduction. Did it hurt the quality of the descriptions otherwise? Sometimes these fixes can make the output worse overall.
That's always a concern. But interestingly, in some cases, they reported that TruthPrint actually improved the general quality of the captions, measured by things like the BLEU score.
Oh, wow. So it didn't just make them more truthful, but maybe more coherent or relevant, too.
It seems possible. Perhaps by avoiding those weird hallucinatory detours, the model stays more focused on describing what's actually there, leading to better overall captions. They also highlighted results on the POPE benchmark, showing really high precision, which again points back to that high specificity. It's good at identifying the actual hallucinations.
And the Calm Hallu part, did the transfer work?
Yes, they showed good transferability results. The approach was effective even when transferring between models with different vision backbones or different hidden state dimensions, suggesting the method is quite robust.
Nice. Did they dig into the details, like which parts of the model were most important?
They did. They ran ablation studies, tweaking various parameters, the threshold for intervention, the size of the subspace they looked at, how far back they traced, which specific layers of the network to use.
Any key findings there?
One interesting bit was that they found the middle layers of the large language model, part of the LVLM, seemed to contain the most useful information for distinguishing truthful from hallucinated states.
Middle layers. That rings a bell. Hasn't similar stuff been found in regular LLMs too? About where certain types of knowledge or reasoning happen?
Yes, exactly. There's a growing body of work suggesting that different layers specialize in different aspects of processing, and the middle layers often seem crucial for more abstract semantic understanding. It's neat to see a similar pattern emerging in these multimodal models in the context of hallucination.
Fascinating. And practically speaking, is this TruthPrint thing computationally heavy? Does it slow the model down a lot?
According to the paper, the computational overhead is quite modest. They claimed it's comparable to standard greedy decoding, which is the typical fast way models generate text. So it seems potentially quite practical.
Okay, that's important for real-world use. So stepping back a bit, how does this fit into the bigger picture of AI research? You mentioned the connection to LLM interpretability.
Right. I mean, trying to understand what's going on inside neural networks isn't new. There's a long history going back decades of trying to figure out what individual neurons learn, how concepts are represented.
Probing the black box.
Exactly. And more recently with LLMs, there's been intense focus on techniques like knowledge editing, locating facts within the network, and generally trying to make their reasoning more transparent. This paper is very much in that vein, extending those interpretability questions to the vision language domain.
How does it compare to other ways people have tried to tackle LVLM hallucinations before?
Well, earlier approaches often relied on more, let's say, statistical or surface level signals. Things like looking at attention patterns where the model looks in the image when generating a word, or analyzing certain properties of the model's internal activations like rope decay, without necessarily building a direct model of truthfulness in the hidden states.
So those were more correlational, maybe? This seems more direct?
You could say that. This work tries to establish a more direct link between the core computational state of the model, the hidden state vector just before generation, and the likelihood of producing a hallucination. It feels like a step towards a more mechanistic understanding.
Okay, so let's try and summarize the key takeaways for everyone listening. What are the absolute must-know points from this paper?
I'd say three main things. First, the internal states of LVLMs do contain valuable signals about potential hallucinations, right down to the specific token level, and these signals have high specificity.
Right, the reliable alarm bell.
Second, there seem to be universal, or at least common, patterns related to hallucination across different LVLM architectures, hiding in these latent subspaces.
This shared hallucination language.
And third, by identifying these patterns and specifically targeting them, we can create intervention strategies, like TruthPrint, that actively guide the model during generation to significantly reduce hallucinations without necessarily wrecking the overall quality.
And that balance seems key, reducing the bad stuff while keeping the good.
Precisely. It's not just about suppression, it's about guided generation towards more factual outputs.
So the real-world implications. We touched on this, but it's worth revisiting. How big a deal is reducing these hallucinations?
Oh, it's huge.
Yeah.
Think about any application where you need to trust what the AI is telling you about the visual world. Image captioning for accessibility, visual question answering for information retrieval, even more complex tasks like robot navigation or interaction based on visual input.
If the AI is just making things up, none of that works reliably.
Exactly. Hallucinations directly undermine trust and utility. In safety-critical areas, it could be dangerous. Even in less critical ones, it's just annoying and makes the AI less helpful.
Yeah.
Getting factual grounding right is fundamental.
So this kind of research is really pushing towards AI assistants and other systems that we can actually, depend on more.
That's the goal. More reliable, more trustworthy multimodal AI. It's a really important direction.
Absolutely. Okay, great summary. Now, let's shift gears slightly to our novel notions segment. This is where we kind of riff on the paper, maybe brainstorm some future research ideas it sparks.
Always a fun part. What's on your mind?
Well, thinking about TruthPrint and its intervention threshold, that value they use.
The point at which it decides, okay, this looks like a hallucination, time to step in.
Right. They seem to use a fixed threshold in the paper, perhaps tuned via experiments. But what if that threshold could be dynamic?
Dynamic how? Adjusted based on what?
Based on the context. Maybe the specific task the LVLM is doing, or even the type of image it's looking at.
Interesting. Give me an example.
Okay, imagine using an LVLM to analyze medical scans. Accuracy there is paramount, right? Even a tiny hallucinated detail could be misleading.
Absolutely critical.
So in that context, maybe you'd want a very, very strict threshold, a high bar for truthfulness. You'd tell the system, look, be really sure before you say anything, even if that means the descriptions become less detailed overall, more cautious.
Okay, prioritize safety and accuracy above all else. Makes sense.
But now contrast that with using an LVLM to generate, say, creative captions for artwork or social media photos. There, maybe you want a bit more imagination, a bit more flair.
You might tolerate something that's not strictly, literally true if it's evocative or funny.
Exactly. So for that task, you might use a higher threshold, allowing the model more creative freedom, accepting a bit more risk of minor factual deviations for the sake of style or engagement.
So tailoring the truthfulness requirement to the application's needs.
Yeah.
That feels like a very practical extension.
Right. It connects to ideas like task-specific adaptation and also uncertainty quantification. Maybe the model's own confidence level about the image could influence the threshold too. Like if the image is super ambiguous or blurry.
You want it to be more cautious, set a lower threshold automatically.
Yeah. The paper already shows this trade-off between the threshold, truthfulness, and diversity. So analyzing that trade-off in relation to task demands or image characteristics seems like a natural next step.
Yeah.
Could make LVLMs much more adaptable.
I like that. More context-aware AI. What's your second notion?
This one's maybe a bit more out there. It focuses on that hallucination subspace. They found the internal representation patterns associated with making stuff up.
Okay, the shared patterns across models.
What if, instead of just trying to detect when the model enters that space, we actually try to model that space better? What if we trained another model specifically to generate plausible sounding hallucinations?
Train a model to be good at making mistakes. Why would we do that?
To build a better detector. Think of it like adversarial training. If we had a generator model that got really good at creating convincing, hard-to-spot hallucinations based on the patterns seen in real LVLMs,
Then we could train our detector model, like TruthPrint or an evolution of it, against that generator. The detector would have to learn to spot even subtle or tricky hallucinations.
exactly. It's like creating a sparring partner for your hallucination detector. The generator tries to fool it by mimicking the LVLM's failure modes, and the detector gets stronger by learning to recognize those specific failure patterns in the internal states.
So you're leveraging the understanding of the negative space, the hallucination patterns, to improve the recognition of the positive space, the truthful generation.
Precisely. It merges this internal state analysis with adversarial techniques. By explicitly modeling what makes a convincing hallucination for this kind of model, we might uncover subtle signals or weaknesses that current detectors miss. It could lead to much more robust systems.
That's a fascinating, almost counterintuitive idea. Using generative modeling of errors to improve error detection. It definitely feels novel.
Of course, just spitballing here. These are speculative ideas. Food for thought.
But stimulating food for thought, that's the point of this segment.
Well, this has been a really productive deep dive into the TruthPrint paper. It feels like a genuinely significant contribution to making LVLMs more reliable.
Agreed. It tackles a core problem with a very clever internals-focused approach. We definitely recommend checking out the full paper if this piqued. Your interest link will be in the description, as always.
It's packed with more technical details and results than we could cover here.
Absolutely. A solid piece of research.
And it really leaves you thinking, doesn't it? As these multimodal models get woven into more parts of our lives, how critical will it be to truly understand what's happening inside them, to ensure we can actually trust what they tell us about the world?
That feels like the central question for the next phase of AI development, building trust through understanding.
Indeed. Well, thanks for joining us for this deep dive here on Talk Tensors. We'll catch you next time.